Ja, så var klokken 11, og jeg tænker, vi kan gå i gang. Rigtig meget velkommen til det fjerde webinar i serien omkring 3D-print af store emner. I dag skal det så handle om hybridmaskiner og pulverbaseret dette. Så det er det fjerde webinar i serien. Velkommen tilbage til jer, der har deltaget tidligere, og velkommen til jer, der deltager for første gang. I dag har vi med os Dirk fra DMG Mori, og jeg vil også forklare lidt om Force Technology sin setup, som også kan bruge pulverbaseret dag i dag. Webinar-serien her, det er jo en effekt af det partnernetværk, vi har, som hedder Aimlink. Aimlink er jo bygget op af over 30 virksomheder, som alle har sine spidskompetencer inden for bestemte områder, som alle kan relatere til additiv fremstilling. Så vi har alt fra keramisk til metal, til polymer, og til kvalitetssikring og scanning og afskaffelse. Aimlink fungerer jo på den måde, at der er lige meget, hvor man er i fasen, om man er på idéfasen, design, pilotserien, produktion, decommissioning. Vi kan komme ind, vi kan hjælpe jer med ideen, vi kan hjælpe jer med designet, vi kan hjælpe jer med produktionen, enten med at producere for jer, eller tilknytte en af vores partnere, der sælger maskiner, som så kan sælge en maskine til jer, så I kan lave in-house produktion. Eller afskaffelsen fra det bæredygtige perspektiv. Vi har en LinkedIn-side, hvor vi lægger op nogle cases, vi præsenterer vores partner. Så der vil jeg helt klart anbefale I følger. Der vil der også komme senere invitationer til nye webinarer eller andre relevante ting inden for 3D-print. Sidst så havde vi jo besøg af Thomas van Glabbeck fra MX3D, som forklarer lidt om, hvordan man bruger robotter og en svejsepistol til at svejse emner, som med at bruge svejsning som en 3D-print-metode. Og vi går så videre i dag til det pulverbaserede del, hvor vi har Dirk fra DMG Mori. Han er salgschef for dele af Europa, og har meget god viden omkring det her, og vil så lave en god præsentation om de maskiner og de muligheder, som deres maskiner har. Hvis man har spørgsmål eller andet, så må man gerne vente til sidst, hvor vi tager en opsamling af alle spørgsmål, hvor Dirk eller jeg eller nogen andre kan svare på dem, hvis jeg har den. So Dirk, are you with us?
Yes, of course.
Perfect. Then I'll leave the screen to you.
Okay.
So you can share and start your presentation.
Yes, that's a pleasure. Thank you for having me. Good morning to everyone. As Ivar said, my name is Dirk Rode, and I'm the product sales manager of DMG Mori for the so-called advanced technologies. What does this mean? I will show in my presentation. A second to start it. Yes, I work since 2013 for DMG Mori as a product sales manager. Product sales manager is a product specialist who is supporting our area sales engineers when it comes to certain projects, to special requests. You must understand that an area sales manager of DMG Mori has the full range of all machines, all services, all digital products in his portfolio, and he knows a lot, but as soon as it comes a little bit deeper into the technology, into the processes, he has the possibility to call me in. He has 200 products, I have 10 products, so I know much more about my 10 products than he does, because it's not his job, right? I'm responsible for Scandinavia, for England, Scotland, Ireland, Benelux, and the northwestern part of Germany, and I'm supporting 65 area sales engineers right now. Yeah, very brief introduction. Who does not know DMG Mori? It's the former Deckel Mau Gildemeister and Mori Saiki company, which is now completely together, owned by Dr. Mori Masahiko Mori, still located in Japan. Yeah, we have the green and the red fraction in our DMG Mori world. The green is more or less responsible for Europe and China, and Japan is responsible more or less for Asia and North American market. We have both headquarters, DMG, still in Bielefeld, Germany, with Mr. Tönnes as the chairman of the board, and of course in Tokyo, Japan, where Mr. Mori is located. Over 12,000 employees, over 100,000 customers, and many R&D centers for the different technologies for milling, turning, additive manufacturing, ultrasonic, SLM, and of course the DED technology, which is the laser tech fraction that is based in Fronten in southern Germany. In Fronten, we do not only work for or with DED. We have many different laser machines in our portfolio. It's power drilling, it's shaping for texturing surfaces. It is a precision tool in which we finish PCD or CBN tools with a laser, as well as, of course, the DED technology. DMG Mori is working in both industrial focused fields of printing. It's on one end, it's the SLM technology with the Realizer company we recently bought, or we bought in 2017, and of course the DED, the direct energy deposition. Therefore, we have a portfolio of now on 10 different machines overall for additive manufacturing, but we would focus on the DED technology. Everybody who does not really know about the process, the SLM is you have a powder bed, and typically the laser on top, and you have a 2D process. You weld layer per layer and add new powder to it. That is for very, very fine and detailed structures, but typically not for big parts. And you are hooked up to only one powder in it because you have the powder bed. The DED works different to that. You have kind of a nozzle head in the center. You have the laser to bring the heat to result a melt pool. There you blow the powder onto the melt pool, and that is more or less covered by a shield gas. So that's a laser welding process. Available in many different applications. Till later on, there are robot applications available. Some have more the size of the part in focus. We focus more on the hybrid background of it. Hybrid means additive and subtractive in a wild mix. So first subtractive, clean destroyed areas, add material, and in the third step you finish the added material. Yeah, sorry, my presentation was a little bit slow. Here's this typical SLM process where you add powder layer per powder layer, and then you weld the powder with the laser from the top. And this is the DED application where really have a laser welding where you shoot or blow the powder onto the melt point and build your parts. DED is not a developing status anymore. This overview is a little bit over a year old. Right now we are at over 80 installed machines worldwide as a basis. The first customers, of course, were universities and research and development centers, but it's now definitely in the industry, and it's a weapon. You will see that later for every quick repairs, fine details, print out. Here are 3 of 5 available Lasertec DED machines. They are all based on our 5-axis milling machines. So the hybrid, Lasertec 65 3D hybrid and Lasertec 125 hybrid, they are fully capable 5-axis milling machines with absolutely no restrictions or limits or no differences compared to a standard milling machine. That's a DMU 65 monoblock or a DMU 125 monoblock machine. Who knows our machines? And we simply add the DED technology. On the right hand here, you see the attachment, because the machine housing itself is not big enough to cover the full laser head with the transfer module in there and the powder storage and everything. But the 125 is big enough that it was possible to locate everything in the original housing of the machine. Yeah, working areas, hybrid 400 millimeters height. It's a little bit less than the DED only. This is a non-hybrid machine. It's only for DED works. That's resulting due to the laser head. We have a little bit reduced height and a 500 millimeter diameter roughly. And the Lasertec 125 is almost 750 and has 1250 millimeters in diameter, up to 2 tons. We also have, that's brand new now, we have a first installation these days running in the United States. That's a turn mill center, up to 6 meters in between the spindles, with a maximum diameter of 1070 millimeters. This machine, I mean, you see the relation or the ratio between the operator shown on the panel and the machine size. This is really, really big. And right now we see the focus on coatings, on shafts, every kind of shafts and crankshafts and whatever is long and requires a coverage. And this summer there's a new one upcoming, located between the 125 and the 6600. Few rough numbers. We have a world premiere in 3 months, so right now we do not show much more about it. Before we have a look on for what the machines are used, the user cases, I would like to point on a very important portion of this DED technology to make it capable of a usage in your industrial environment. The machine, the Lasertec 65, was presented in 2013 already, but over the last 7.5 years we found out that there are some minor mistakes which result a bad part at the end. Now we are in a situation that we have almost everything monitored in the machine itself, and mainly it is all around the powder. What we have is a powder mass flow calibration unit with a little scale in the back. So the machine is asked to, for example, feed 50 grams of powder, and we feed the powder and the scale is automatically weighing it and reflect the result back to the machine, that the powder flow is self-calibrated. Then we have in the powder feeding a mass flow monitoring. because it can happen if the machine stands still for a long time, or you take an old powder which is just a little bit wet, so it's gonna sticky, or the powder quality is not that good, that the powder feeder feeds, but no powder is coming to the nozzle, and there's no welding process. It's just the laser, yeah, the laser burning on your build plate or whatever. Then we have the so-called working distance monitoring. This has to do, you see here in the screen, I can zoom this up a little bit. When you add material, you can program, which is in this case Siemens NX. You can program, tells the machine, okay, with every layer you have an increase of, let's say, 1 millimeter. But if this is not right, and you have a full print of a part 200 millimeters high, and with every millimeter you have additional 0.1 millimeter, after 100 layers you are way out of the range. So the part grows to the nozzle, and you do not have the melt pool anymore that you want. So that's why the distance is controlled, monitored, and runs into a certain range in between, let's say, 14 and 15 millimeters. If it runs out of that, we assume that this is a mistake, and the machine will stop for safety reasons. And what we have two temperature checks is, one check is here on the top left. We are scanning, or we are checking the heat impact into the part and into the clamping, as well as into the table, that everybody, or that the operator, everybody knows how the heat impact into the clamping is. In this case, it says yes, no. The heat is not too bad, but as soon as start, the heat goes tremendously into the table of the machine, then you would have to stop the machine. And we have a melt pool monitoring with a self-adjusting leveling of the machine during the process, and you can every time adjust your speed, your gas flow, as well as your laser force on the operator panel during the process. Yeah. That was simply and short about the machines, about the technology, and there's much more, but Ivar and I agreed to give just a rough overview, and who is really interested, we have a question and answer session after the presentations, as well as, of course, we'll share my contact data, so I would be happy to really get a feedback from you. Most important thing, for what is it? Our DED machines mainly do not focus a full print of very, very big parts. You must understand, we are focusing the precise build and precise replacement and precise repair of existing parts, or a very precise coating of forms, molds, shafts, or whatever needs a long life or a hard coating surface. Our DED machine right now is capable of a performance like 700-800 grams per hour. The big turn mill machine is capable of printing up to 4 kilograms an hour. That's a result due to the size, right? You cannot work with a couple of 100 grams on such a big machine. Here are some samples for tooling. Cast industry, especially die cast industry, is extremely interesting for that, and as well chemical plants, etc. See, this valve housing is made from a chemical company. They have plants all over the world. Some of these housings are over 40 years old. You know, everybody knows these housings, and there are no casts available anymore. There are no drawings, nothing. old standard seals in there. Everything was custom. So what they do is they scan where it sits. And they have the distance between the flanges. They know the fixing points, and the rest of it they redesign based on standard industry norms, and simply print the same flanges and actualize the rest of the valve. And this is a full print on the machine. In this case, very special because it's a mix of additive and subtractive work. See it here in the right bottom, how it builds up from top down. Print time of this part is almost 30 kilogram, and it's 56 hours. So within 2 days you have a new machined valve as a replacement. This one is extremely fast. It's a cutter knife repair setup of the machine. They print the soft base with the tool steel ferro 44, comes out with 44 Rockwell, and then you have a so-called M2. That's a high-speed cutting steel. Typically, you cannot weld high-speed cutting steels, but it's available as a powder and works great in the machine. So we have a 2 millimeter layer hard cover on this knife that comes out of the machine with 63 Rockwell, ready for the installation into the tool back again. Total print time of this part here right in the bottom, including the hard coverage and machining, is 6.5 hours. So you get completely away from this machine tourism where you machine the destroyed sections off and move it to the next machine or to the hand welding shop, and then relax or stress relieve it and then finish it. And it takes typically for this customers 3 to 4 days for replacement. With this case, he has it in less than a shift, completely replaced and ready for the assembly. This is a part to show we developed on our own, a tube in tube, but this is one of the best samples. DD technology is capable of handling in standard 2 different materials. Compared to the SLM, you have one big powder bed where your powder is in, you cannot mix the powder. But here, you can imagine that we blow the powder to the nozzle, and due to this blowing process, we can make a clean shot and then switch the valve and feed a second powder to the nozzle. So here you have a mix of stainless steel and bronze in the middle. It's a great combination, and right now we are able to make a mix up to 4 different materials. What is possible? A few slides later, I can show you and explain why it might be interesting to use a powder mix. This is a part we print for one of our own machine. It's a Lasertec 400G shape machine for texturing molds, surface texturing of molds. This is we print everything what you can see here, and our build plate is the big base plate of it. And here on the right bottom, you see the finished part of it. We keep it here with a rough surface, as you can see here, because it's on our own product too, so it gives us a little bit advertisement and have a coverage. But the intention was to have a lightweight, very functional machine part to carry the laser optics on the machine, on the spindle position. This is one of the most interesting parts for repairs. It's die cast molds and die cast cores and everything. So the core comes used into the machine, and then we have here top left. That's a used part. We are focusing the sections where the highest wear of the part is. We get the surface material up to 3 millimeters off, and then add the material, replace the used and the broken sections, and then finish it in the machine. It is an extremely fast, high reliable repair of these molds in one shot, in one machine, with only one clamping position. It saves so much time, and due to that, so much costs, and the possibility of using a harder material than the core is itself typically. So we work here with the M2 63 Rockwell, gives a 3 times higher lifetime of the part. This is what I mentioned with precision. Excuse me. I'm sorry. The precision of the machine is, or typically the mass or weight is the opposite of precision. In this case here, you have a die-cast core with used sections, and what you can see here is that we subtractive. We mill the used sections away, and then we add the material and finish it in one machine. So the existing process is the preheating for the manual repair welding. Then you have the cool down, the milling again, and a total loss of 2 days to repair this core. On our machine, you have only one setup. You put the core into the machine, machine it off, weld it, have a few minutes cool down, and then finish it in the milling process. Why is it not necessary to preheat this part? The heat impact of the laser is such a small dot that the heat impact of the overall part is very, very little. So you typically do not have too much stress compared to manual repair welding on that, which is also very rough. You weld big areas and you lose many details, and everything has to be machined off again. This is the same, probably better shown in the pictures. Top left is in red is the focused item that has to be replaced. Top right, you see this empty space. This rib has been removed by a milling tool. Then we add the item again, and bottom right, there is a finished section of it with a fully repaired rib in this tool. This company, Friedrich Deutsch, is located in Eastern Austria, and only for die-cast repairs, they have, since last year, 3 LaserTech 65 machines to do exactly what you can see here in the photos. Yeah, that's another story, impeller, full build of impellers with a complete mix of additive and subtractive machining. You know that the radius of the impeller shovels are limited to what is feasible or what is machinable with milling tools, right? But with this machine, you are not limited by that. The radius or the angles of the shovels can be much tighter, because before you close the impeller, you can finish the full surfaces of it. This is a short overview of all available, of all parameters for the material that is available. In general, with this machine, we can work with almost every powder or with almost every material that is weldable. What you can see here is what we have a lot of experience with and where we have the parameters Yes, one note, one keynote on that. The powder of DED is much more bigger than the SLM powder. No, typically it's not airborne. We recommend to use a mask and gloves because there might be smaller particles there, but typically the powder, the smallest ball size is 55 micron. The maximum ball size of SLM is typically 40 micron, something around that. So the powder is much rougher. I know I have to speed up a little bit. Here's what you can see, material mix right in the middle. There's this stainless steel copper mix again. It's always a great combination, and you can change the material layer by layer by layer. On the right side, there's so-called graded materials. We fade with the material. So at the bottom, you have the 1% maybe stainless steel, and then you fade over to a tool steel to give an extremely smooth transition, or you take austenitic steels and non-austenitic steels to increase the magnetic force of the item itself. Many functions of it are possible. Then there's a special kind of sorry, I'm missing the word, excuse me. The copper bronze, it's a mix. Okay. I'm sorry, I'm singing, and it doesn't matter. That is very often used, bronze and this alternative to copper. It's a little bit more rigid, and it's very often used in combination with die-cast cores, and combination of hard surface, a support with bronze, and cooling channels in there. You see that here in the top right. You have the hard coverage of the core, and then you have the bronze to feed the heat away, and cooling channels right in the middle. This saves unbelievable so much money due to that. It is due to the process times of the part, especially in this case. They reduce the scrap by over 3% a year, and that is resulting 180,000 euros of scrap part they simply save. That's it. And the lifetime of this tool is more than double what the original one with a pure tool steel was. It's right. It's just a rough overview. If you are interested in that, contact us, especially for die-cast molds, repairs, and everything, coatings. It's a real weapon. Or different thinking here in the middle from Scheffler. That's a DIN norm standard part from a catalog. In the past, they had a block of steel and they machined all around these little rods away. Now they think the opposite way. They have the base plate and simply add the rods and then finish it. Saves 70% of the time again. So that was me. I hope it was interesting and not too fast, and many details, but not too many details. And I would be happy if you have any questions, require further informations or whatever, feel free to get in contact. I believe that Ivar will share contact data as well as the webinar itself. And I'm now curious what I can learn from the other speakers.
Yeah.
Thank you very much. Thank you.
Thank you very much, Dirk. Great presentation, a very thorough explanation of all your machines, but also the technology itself. So hopefully it has inspired someone. I'll share my screen. So yeah, I'll jump over because a lot of you know we also have a similar setup on Linux, but it's not the same. It's used on an industrial robot instead. We have the precision rate of up to 10 kilo, and as Dirk mentioned, we may have the higher focus on the size, definitely. But it's the same principle of laser and powder welding. So we use the same. We have 2 powder feeders, which means that we can use the same material in both, or we can mix them if needed. So there are a lot of possibilities with the materials there. We can also do cladding on inside of pipes. So we can do with powder-based DED. We can also do it with a laser and wire. We could do it with arc welding and wire. But we can also do laser welding. So our machine, not to compare it to DMG, but our machine is maybe a more multifunctional machine. So we do aim for the big size and a lot of remanufacturing as well. So if there's any question on to our setup or DMG machines, feel free to come with some questions if you have.
My name is Sten Nielsen.
Hi, Sten.
Can you hear me?
Yes, we can.
Try to put the camera on, but it's not. Yes, I think the camera is on now, maybe. Yes.
I can see you.
My name is Sten Nielsen. I'm a colleague to Ivar and at Forge Technology, and I have worked with laser technology for many years. I have a few questions for Dirk. Thank you, Dirk, for a very nice presentation. I'm very impressed of your equipment. I think it's now more than 40 years ago since the first laser cladding was demonstrated. That was at that time it was with CO2 lasers. And even though it was very primitive compared to what you can do today, it has been done. It has been utilized industrially in a small scale over many years. But due to the development of technology, the equipment, high-class equipment is now available. And this is, of course, due to the development of lasers and the nozzles, powder nozzles, fiber technology, but also, computer technology, programming, and so on. So that's why we now have these very impressive machines. I have a questions regarding, maybe these questions are a little bit technical, but I would like to know, I could see that the SLM machines, you are working with around 400 watts, which is delivered from a single fiber laser, due to have a quality of the beam which is suitable for this kind of process. Which kind of lasers do you use in your DED machines, and what power levels do you use, and what is the fiber diameter? Is that something that you know?
Yes, absolutely. Yeah, as you said, the laser, the SLM, the small SLM has a 400 watt laser, the big SLM has 600, and the duals double 600. With our DED machines, LaserTech 65 and 125, we have a 3000 watt laser, 3 kV laser, and the spot size is focusable. The spot size diameter is, I don't want to tell you something wrong, but the smallest thin wall you can build up, it's 1.5 millimeters.
But what type of laser is it? Is you always deliver the same type of laser, Trumpf, or it's not a disc laser?
No, it's a fiber laser, and we use IPG lasers and we use Trumpf lasers, so we don't have any exotic lasers.
Okay.
We typically tell the customer which laser is installed when he purchases the machine. I'm sorry.
Okay. So,
this is a little bit a development advantage we have, yeah.
okay.
But we have IPG and Trumpf lasers in our different machines. You know, we work with 20-watt texturing shaping lasers, femto laser, and power drill is up to 23,000 watt in peak for drilling holes. In this case, the 3,000 watt laser.
I actually thought that you were using diode lasers for this. It's not diode lasers you have in. No, okay.
No.
So you are even in the DED you are able to make very narrow wall thicknesses.
Yes.
Yeah.
Absolutely. Okay. As I said, steep walls, yes, and the thinnest wall you can weld or print with the 65 or 125 is 1.5 millimeters. If you need it thinner, feel free to change the tool, unload the laser head, and load the milling tool, and then mill it down to whatever you need.
Can you vary the wall thickness during processing with some kind of zoom technology, or how can you change the focal diameter during processing?
No.
Or do you always have the same wall thickness?
Yeah, we typically have the same wall thickness. What we have is a 1.6 millimeter nozzle diameter and a 3.2 millimeter nozzle diameter. So for the 3.2, it's for full prints where you do not focus the precision. And we widen up the focus of the laser a little bit, that you have a wider line to weld up. But in general, you cannot change the thickness in the process itself. You have to change then the nozzle, and that has to be done manually.
What about the powder nozzle and the powder feeding equipment? Is that your own design, or is
Yes.
it's not GTV or Trumpf design?
No, it's our own design.
Also the nozzle. Okay.
Yes.
Is it the same principle that you have, for example, 3 or 6 or 9 holes where the powder is coming out?
No, we have a dosing system.
Is that a ring? Or?
Yeah, it's a kind of. Hold on, I can show you an animation of it. Give me a second, please. Go. I have to find it first. Yeah, always when you. There we go. I would take the. I can show you in a video. That is really, it's then really easy to understand.
Okay. And this is your own design?
Yes, that is our own design.
Okay. You have 2 powder. Oh, there's more than, yeah.
Yeah. So there we go. Here we're back again.
Yeah. Okay. So you have different kind of nozzles, so you can.
Yeah, exactly.
With different ports. Okay. I don't know if there are other people who want to make questions also, but I have I could go to the materials. You showed some very good materials that you have experience with. If you should give me 3 materials which you would not recommend to use, could you do that? I think, for example, have you any experience with aluminum, for example, or other kind of materials where you have difficulties? Could you tell me that, because then we don't have to start there.
Yes. And due to the fact that our machines are based on 5-axis milling machines, they are sealed for the coolant water, but they are not sealed for the gas. And I would say the build chamber is extremely big, of course, due to the machine size. Therefore, it's not possible to work under a 100% shield gas environment like argon, and reactive materials like titanium, aluminum on this machine is not possible.
Okay.
Yeah, that's one of the most important limitation for that machine. Titanium, aluminum, they are so-called reactive materials. They burn typically when they get in contact with oxygen, and you have to handle it under or with almost no oxygen. In an SLM process, it's very easy because it's a complete sealed small build chamber. But in our machines, you have seen, and you can imagine the size of the machine, it's not possible to pump the full working area full with argon. We made tests in the past where we had a kind of a plastic bag between or covering the rotating table and covering the nozzle and everything. And we pumped up to 3 bars of argon into this plastic bag and tried to print titanium on the machine, but we still saw this blue shiny oxidation. So we still had some rests of oxygen in there, and which the titanium reacted with.
Okay, so it's okay. So it's due to it's not possible to make a good gas protection. Okay.
Yeah, that's the biggest problem.
When you are talking about burning and spatter and so on, how do you protect your nozzle and optics from spatter going back to contaminate? Do you have any sensors, or how do you control that? Yeah,
we have. This is what I would like to share this again.
Yeah, I can see we have 2 questions from the chat, and we're about to run out of time. So
okay. So this was last question from me. Okay.
That's fine. There we go. We have this nozzle adhesion detection. Yeah, with a camera looking through the center of the nozzle, we can detect that here at the bottom you see these 2 red balls.
Yeah,
that's sticking particles.
And the shielding glass or on the nozzle?
That's at the end of the nozzle. The shielding glass, it's when you have the nozzle here, the shielding glass, it's way behind. It's not in front of the nozzle, it's way behind the nozzle. Typically, we don't get much trouble with the shielding gas. This is a real attachment to the end of the nozzle, what you can see here. In typical production environment, you do not get this very, very often. But when you are in research development, trying different powders or many new situations of it, then it happens more often. Yeah, and you can adjust how big this is allowed, because just a little bit doesn't affect your powder stream a lot. But as soon as this starts growing, it will direct your powder to a different, or you need the powder in the melt pool, but when you have the adhesion, your powder is blown anywhere, not to the melt pool, so your welding result will be bad.
Okay, but how do you control the contamination of the optics? Do you have any
the
optics in the?
Yeah, we have the camera looking through. Oh, this is the center of the laser. Yeah. When something is going wrong, or with the optic is too dirty or whatever, you would see it with the same detection camera. What you can see here on top.
Okay.
Yeah.
Thank you.
Yeah, but the glass of the optic you typically change within the yearly maintenance only.
Okay. Thank you.
Perfect. Thank you very much for your insights, Sten. It's always a pleasure. Share my screen again, and we have 2 questions from the chat. Is there any difference in the material isotropy between WAM and DED, particularly tensile strength and elongation? It's minimal.
No, almost no. Due to the high process stability and existing and developed parameters, it's not better or worse what you can do with other weldings. It's a real welding process. I jumped over this a little bit. You can see it here. You see here the different lines of the welding process itself. Here the same. Don't be scared about the dots. It's from hardness testing. How the hardness affects. It's a typical stable welding process, and it's reliable. And once the process has been figured out, you can throw one part after the other and really manufacture, code, repair on an industrial basis. You don't need care about any process parameter or whatever that it might be worse. What it can affect is what we try to prevent with our calibration, that we are sure that always enough powder is coming in the right, or that the powder mass is correct, that we have the right nozzle distance to the part, and that the melt pool is still, you can see that, whoop, that was a little bit fast. You can see that here. You can even see in which direction this is moving. Yeah, so precise it is. And once the parameter, everything has been checked and the process is running, then it's a very reliable welding process.
Yeah, we also have the same type of camera to ensure that we are getting enough of everything. Thank you. So yeah, Satish, I think that's an answer. It doesn't affect the. It's an isotropic result, very stable. Let's see, Magdalena, one of my coworkers, is asking, how do you ensure a smooth, defect-free, for example, cracks because of various thermal expansions transition between one material and another? Which parameters do you have a focus in order to avoid defects?
Yeah, that's a good question. The point on that is it's simply testing. All materials you have seen, the combination is possible. So coverage with M2 on the ferro steel and work with bronze, and that all works really good together. The stress is certainly a question, but the stress is not as big as you know it from probably hand welding, as I already said. The heat impact of hand welding is much more higher than working with a 1.5 millimeter melting pool on that. When you're really interested, you're always invited to come to front to see the machine working, see more samples of it, and then standing beside the machine, you see that really the area around the melting point is a really small area which is glowing or gluing. And thin walls in a high structure, you have to go slowly, reduce the laser heat, have the heat impact very, very little. Completely stress relief, depending on material. Yes, typically some must be stress relief depending on geometry, some not. For all repairs, we see that the repair area is so small that it doesn't have a full impact on the part. When you have a full print, you would take it off, stress relieve it, and then machine it, definitely, to avoid any trouble which is coming later from bending or deforming the part due to the heat impact there. But that's typical in every welding process and also with every other additive manufacturing process like SLM or DD, doesn't matter. It's all the same, but a good question because you have to think about.
Yeah, I think that also cover, or if she has a follow-up question, do you play mostly with laser power? I mean, we also do a lot of parameter testing where we change the laser power, the feed rate, the print speed, and everything. Is that any different to your machine? Which parameters do you focus mostly on?
No, that's the same. It has to do feed rate, speed, and laser power. Laser power itself is adjusting. I said that we have a temperature watcher of the melt pool. If this is gonna go too big or the color change in the manner that you don't want, laser power is reducing automatically, also depending on the geometry. But customer who get the machine get all our parameters, so we don't deal with parameters or so. We are very, very open. Even with the we have every year at the Formnext in Frankfurt, we have a LaserTech DED user meeting. So every DED customer is invited. Come in, we have a nice conference room, pretty big. We have over 30, 40 customers there, and they speak really open about experiences, what could help for the daily work. So give us a feedback as well. And it's like, at that day, it's like a family, even they are competitors on the other end.
Yeah, I do remember when me and Peter Tommy visited Formnext, very amazing stand with a cafe and everything. So I definitely recommend anybody listening today that if you're going to a conference, go to Formnext. It's an amazing big conference where you get your hands on everything 3D print related.
Yeah, absolutely.
Let's see, we have, I think we can manage one final questions before the wrap up here from John. DMG manufacture also systems with combined MIG welding power source CMT. Have you sold such a system? Or is there anything you can tell me about this option? Well, you don't do, well, that's in the WAM process.
No.
Should be.
We are thinking about it. Because with the LaserTech 125 and the LaserTech 6600, we're still limited to below 1 kilogram per hour build rate. Yeah, but with the LaserTech 6600, that is a project together with Japanese colleagues. They totally redesigned our powder nozzle system and how it works and how everything, so we can increase up to 3 and 4 kilogram per hour. Before that, we were thinking about a wire, so WAM, in our machine to bring a high volume out, because we would like to do more in the forging industry. The forging industry requires an incredible high amount of volume in the forging dies due to the forces and the heat impact. We are not able to do it with our standard powder nozzle, 600, 700, 800 grams per hour. Yeah, so we were thinking about it, but we didn't realize it because now we have a solution for a high volume powder feeder. So we step aside from, for example, WAM. Yeah.
Yeah. But I can also supplement that answer. So the setup that Force has both the option for CMT welding and powder-based DED. So if you have any questions about a multi-purpose system, we can also help answer that if that's of interest. And then let's see if DMG also develops something. I mean, can only go one way in development, and that's forward.
Yeah,
we
know, you know, the robot welding systems. I know them from my past. I was many years in the forging industry, and I know there are many simple robots out who for welding big surface and everything. It's incredible the mess they can really bring with wire onto plates to make a hard cover on a full plater. So how fast they are. That's not our business.
No, everybody focus on the thing. So
Dirk, last question from me. You have these two machines, the DED and the SLM. What are the criteria for choosing the one or the other? Is it only component size, or is it also something with the materials involved, or and maybe also, of course, geometry details and so on? But how do you choose, or how do you for your customers, what are the criteria for selecting the one or the other process?
It's a combination of everything you said.
Okay.
But typically SLM is a very fine, precise, real. It's so-called real printing process. Hybrid parts, repairs, everything that's not possible. It's always a full print. What you can do if you have plain plates, you add features. There is hybrid possible. Titanium, aluminum, SLM, yes. DED, no. And the main reason to go either or, SLM build rates are very little compared to DED. So a single laser SLM machine is capable of a build rate of, let's say, 70, 80 grams an hour. A DED machine is 10 times higher. Yeah. But on the other hand, at the SLM, you have typically nice and smooth surfaces. It's a little bit better than steel casting. And on the DED, you have the optical, you see the welding lines from the outside if you do not machine it. Yeah. Details, SLM, with our SLM 12, it has a 35 micron laser spot. It's possible to print walls below 0.1 millimeter. DED, not below 1.5 millimeters. Yeah. Okay. And a good rule is small parts SLM typically, big parts go for DED or other processes. Yeah.
Okay.
Perfect. Thank you very much. Did that answer your question, Sten?
Yes.
Perfect. Then I'll think we run up. We are a little bit on overtime, but that's fine. People are still in the meeting, so apparently. So the next webinar is going to be about concrete printing, where Simon from 3D Print House is going to come and speak about their cobot printer system, which they sell on a worldwide basis, or for printing in concrete. So it's a very interesting webinar for sure. If you need to get in contact with us, these are my contact details. If you need to get in contact with Dirk or Sten or anyone, please write me an email. I'll share the contacts between you. So yeah, thank you very much for participating. I'll leave the screen on if you want to note the future dates for the remaining 3 webinars. Yeah, again, thank you very much, Dirk, for your presentation.
Pleasure. Thank you very much for listening. And I hope to talk to one or the other of you. Yeah, would be a great success after presenting this in such a big group of people. Thank you.
Yeah. Thank you very much, and have a nice day, everyone.